So let's try drawing the molecular orbital diagram for NO.
So when we usually start with like the BSEPR, we start with like a Lewis dot, and we approach it the same way with this, just to know how many like electrons we're using.
That's a good question. You're asking, should we try to draw the Lewis diagram when doing molecular orbitals? I would say probably that's not necessary. In fact, that might confuse us because we know that actually the Lewis diagram might give a different prediction than the molecular orbital. Yeah, you do need to count the number of electrons, which you would have to do for the Lewis dot structure, but you don't need to do the rest of the process for the Lewis dot structure. So yeah, I would say I wouldn't bother trying to draw the Lewis diagram for NO. You can just count the number of electrons, but let's not worry about the actual Lewis structure.
Would we put them both in, like the electrons in nitrogen, the electrons in oxygen, and then put them together, and then however many we have after that? Would we approach it like that, or is there a certain way we would do it? Or?
Well, we should basically follow the same process that we did before. I'm not sure if I quite followed your question, but we should try to use the same process that we used for the previous cases.
So if we put like, oh, okay, I gotcha.
Okay, well I guess then I don't get it because this is different for oxygen.
That is the one new thing. It's good that you noticed that. So what we know that we have two different patterns of dashes here. We've got one pattern for the elements to the left of my squiggle and one pattern for the elements to the right. Well, here we have a problem because nitrogen's to the left and oxygen's to the right. So what should you do? Well, if you weren't given any information, I don't know, you might have to take a guess. You might be told in the problem. So I'm just looking at the textbook, and in the textbook they used the nitrogen pattern, not the oxygen pattern. But I've never seen like an official explanation for what you do when there's one from the other side of the squiggle. So you might want to see what your instructor does in that case and follow their pattern. But anyway, for this example, they used the pattern for nitrogen. Is that the pattern I have on the board? No, so we're going to have to fix that. Okay. Other than making that fix, though, we should be able to do this the same as the previous problems. Okay. Sounds like we're doing good. How many electrons do we have total?
15.
Yeah. All right, so you saw that, well, I just told you that we were going to use the nitrogen and carbon pattern of dashes. So we flipped the sigma 2p and the pi 2p. Then if you count the electrons here, the oxygen has a different number than the nitrogen. So that gives us 15 overall. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I think this is what you got. Okay. Paramagnetic or diamagnetic?
Paramagnetic.
All right, and what should we plug in for the numbers for the bond order?
10.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, 3, 4, 5. So what did you get as the bond order?
2.5.
2.5. Okay, good. Notice that the total number of electrons here is odd, right? 15. Lewis structures are kind of hard to work with an odd number of electrons because you can't give everybody an octet. But notice that the molecular orbital approach doesn't really care whether the number of electrons is odd or even. So this is another way this is nice and flexible. Okay. So this is the first one that we've done where we had heteronuclear. It's called heteronuclear because there's different nuclei. But you can see the process is not that much different from the homonuclear cases. The only difference is that now the two atoms are contributing different numbers of electrons. And it was a little bit hard to know what pattern to use. Like I said, I've never seen like a general rule for knowing what pattern to use for the heteronuclear case, so I'm just following what the textbook did for this case. So you want to do whatever your instructor does in those cases. Unfortunately, I didn't see any examples of that in your lecture notes. So is this paramagnetic?
Yes. No, yes. Yes.
Yeah. How about if we ionized it? Would it still be paramagnetic?
No.
Yeah.
Because you'd be taking away
Oh,
that one. It's in the, so
Oh, we take that one away?
Yeah.
The pi 2b?
Sorry, yeah. All right, we take away that.
Yeah, what else would we take away? When you take away an electron, you want to take away the highest energy electron you can,
Okay.
right? You always want to take away, when you're putting in electrons, you put them as low as possible, and when you're taking away electrons, you take away electrons as high as possible. So if we took away an electron, this would be the electron we take away, right? And then would that be paramagnetic still?
No.
No, yeah. So this is paramagnetic, but this is diamagnetic.